Hello, welcome back to our second episode on quantum computing with Professor Bindu Bambah, Honorary Senior Professor at the School of Physics, University of Hyderabad. If you haven't watched the first installment of our conversation, you should definitely go back and watch that one first. That is episode 37 before coming back to watch this one. Professor Bambah did her BSc Honours and MSc Honours from Punjab University, Chandigarh, with distinction in all subjects and winning the first class gold medals. She then got her PhD from the Enrico Fermi Institute of the University of Chicago in 1983 under the supervision of Nobel laureate Professor Yoichiro Nambu. She has served as a visiting scientist in the International Center for Theoretical Physics at Trieste in Italy, as a scientific associate at CERN in Geneva, and as a UGC scientist at the University of Madras, Punjab University Chandigarh, and University of Hyderabad, and then as reader at the University of Hyderabad and professor of applied mathematics at Punjab University Chandigarh. Dr. Bambah was awarded the UNESCO ROSTCA Young Scientist Award for South Asia in 1991. She has authored 132 research papers, garnering over 7,600 citations. She has worked on the nature of the quantum chromodynamic vacuum and the physics of strongly interacting systems, on new coherent states in quantum optics, isospin squeezed states, and on the interrelations between particle physics, plasma physics, fluid dynamics, quantum optics, and cosmology. Her theoretical studies on the quark gluon plasma address the problem of thermalization and stability of this plasma. Her recent research interests are in neutrino oscillations and quantum computing. You talked about quantum gates a few minutes ago. So can you give some examples of quantum gates? And also you mentioned an emulator or a simulator, and how is that different from a quantum computer?
Okay, so I come to quantum gates. So remember I talked about the block sphere in my previously, and I showed that if you consider one vector on this block sphere as one of the superposition states of the one qubit state. So all the qubit states are all the states on this sphere. And what is a gate? A gate is going from one state to another. So a gate implements a transformation of the vector on the sphere from one direction to another. Okay, so that is why the sphere is a useful analogy, because you want to take one superposition to another superposition, basically, right? So what is in the sphere? What does that mean? In the sphere, it means rotation from one side to another side. Then the vector changes, right? So what is a quantum gate? A quantum gate takes a qubit from one state to another. So what a quantum gate performs a unitary rotation on the block sphere. So that is what a quantum gate does. Okay, and the way quantum gates do it is by various lasers and various trapped ion sort of gadgets which are there. But basically, they take one qubit state to another qubit state, and so to put a cubic state on a block sphere, we require the idea of quantum gates. So a quantum gate is technically defined as a matrix, because all matrices of 2 by 2 vectors are all rotations of 2 by 2 vectors are represented by matrices. And since there's also a phase, it's a unitary matrix rather than just an orthogonal matrix. And it is such that it takes one state to another state. So if you have a original qubit state as psi and you want to go to another qubit state psi prime, what you have to do is perform a unitary operation on psi. And this unitary operation is what is performed by a gate. Okay? Now let me just show you what these gates actually do. For example, let us say that an arbitrary unitary matrix has this form. So if you want just to rotate from one axis, from one position to another position, then lambda and phi are pi by 2 and minus pi by 2, and the rotation matrix is simply this. So that is called a universal. This is called a universal gate because this embodies all possible gates that can be visualized on a
single
IBM
qubit. There's a single
yeah.
qubit gate.
Yeah. So now for this universal quantum gate, let me just show you particular ones because this is not very helpful. Okay. So so let me start with particular gates. The important ones are C0 gates, Hadamard gates, and phase flip gates. And so I will tell you all the gates. If you have a rotation around the x-axis, that's called a bit flip. That is, it takes you from one direction on x-axis to another direction on the x-axis. So it's like a bit flip. That is, it goes from 0 to 1 or 1 to minus 0 to 1. These are 1 qubit gates. Then there is a phase flip, which is rotation around the z-axis. Then you can create a superposition of 0 and 1 qubit by using something called a Hadamard gate. And then if you have rotation around y-axis, it is a combination of a bit flip and a phase flip. Then with 2 qubit gates, you have a C0 gate that creates an entanglement. Then you have a controlled phase flip gate that controls phase flip of one and not the other. And then you have something called a swap gate, which exchanges 2 qubits. So any quantum algorithm can be built.
You might need to explain some of these. I think you might need to explain some of these a little more detail.
I'm going to explain.
Okay. Yeah.
So all of these are, you can think of these as Lego blocks, and these are the various pieces of one Lego block, and these are the various pieces of how you can connect 2 Lego blocks. And so let us now see. Okay. So let us see what is a Hadamard gate. That is one that when that takes you into a superposition of the state. So a Hadamard gate is an example of the universal quantum gate, which has this form in which theta and phi are given by pi by 2, 0 and pi. And so so now supposing that you act this on the vector 1, 0, okay, then that will take the vector 1, 0 into a linear combination of the vector 1, 0 and 0, 1, right? Because this flips that. So you will get 2 states on the initial state 0. The action of H will give you this linear superposition. On the initial state 1, the action will give you this linear superposition. Okay. So the Hadamard gate is that universal gate that takes that acts on a bit and changes it into a superposition. Okay, a linear superposition. Okay, and to recover the qubit, all you have to do is apply the Hadamard gate twice, because when I do this twice, I will get the identity. All right, so on 0, it gives you 0, and twice application of Hadamard gate gives you 1. Okay, so this is one of the gates. That is the gate that is responsible for creating a superposition state from 2 states. Okay, so basically here this is what the Hadamard gates does. Here is 0, here is 1. You apply the Hadamard gate and it gives you this linear combination of 0 and 1, which is at 45-degree angle here, right? Okay. Similarly, if you have 2 qubits here and you apply the Hadamard gate, then the upper qubit becomes this and the lower one this. So this is the action of so this is rotation and Hadamard gates. Okay, this gives you a superposition. All right. Sorry, this was the rotation gate and this was the Hadamard gate. This is the Hadamard gate acting on 0 and this is the Hadamard gate acting on 1. So basically, as I told you, all these gates are unitary operations on the block sphere, and they're represented by. So then you have something which is called a C0 gate. So let us see what a C0 gate does. So what it does is that this gate, if you start with a single qubit, which if the control qubit is a 1 state, what it does is it flips it takes a qubit and it flips the other the qubit which is not so it flips the target qubit only if it is in the 1 state, and if it is the 0 state, it doesn't flip it. That is the C0 gate. So if you have a state 0, 0, it won't do anything on it. If you have a state 0, 1, again, it won't do anything on the first one. But if you have the first state as 1 and 0, then it will flip the other state that is with it. And here, if you have both states 1, 1, but it will flip the state which is next to the control state. So if you have two qubits like this, one being A being 1 and B being anything 1 or 0, then B will be flipped. If A is 0, then B will not be flipped. So this is for two qubit states, and this is called a C0 gate.
So essentially, B is flipped if A is 1.
Yes, B is flipped if A is 1. Yes.
And B
So
can
this does is this C0 gate is also called the entangling gate. Okay, it entangles the states, and let me just show you.
Okay, and B can also be a superposition state.
Yes, yes, B can also be a superposition state. So, for example, here we have these. So the classical maximally entangled states in quantum physics are called Bell states. Okay, and it is if you have two qubits 0, 0, you operate them. It is C0 gate which produces the Bell states on this. Okay, so if you have your input state 0, 0, then what the C0 gate does is it gives you this linear combination: C0 gate plus Hadamard gate. If you have an input state 0, 1, it gives you 0, 1 and 1, 0. If you have an input state 1, 0, it gives you this one. 1, 1, it gives you this state. So you see, all of these states are maximally entangled states in the sense that they are equal. They have equal probability of being in the two different states. Okay.
So here you're operating with C0 followed by Hadamard?
Hadamard. Okay. C0 followed by Hadamard. Okay, so that is the way of producing Bell states. So, so for example, so this is the mnemonic representation. So for example, let us see. Okay, so here is so you can do it Hadamard and then C0, or C0 and then Hadamard, either one. So this is the quantum circuit which is responsible for taking two input states and producing Bell states from them. One Hadamard gate and one C0 gate. And this is how you represent it on a schematic quantum circuit diagram. Okay, so this is the schematic quantum circuit diagram of a 2-qubit Bell state, and the output states here will be all these Bell states. So this is how a circuit of a quantum computer works, and this is how the gates. This is an example of how the two most important gates, the Hadamard and the C0 gates, one is like a flipping operation, and the other is the superposing operation. Okay, and this is how you produce entangled qubit states. And so this is only for 2 states. So you can just imagine for 10 states how many different Bell states you could produce. So for 2 states, you produced all these states. So for 10 and so on, you can see that 2 to the power 10 and so on, you can produce many, many different states. And so that is what gives you the power of the computing. All right. And so to generate 2-qubit Bell states, we need a measurement circuit also known as Z basis or computational basis. That is, you want to measure it. When you want to measure the state, then you have to have, then you have it represented in the circuit by this figure, which means that the wave function has collapsed to that state. So that is the measurement circuit. Okay, and I will go later into why copying of qubit states is not allowed and all these things, which are important for the security of the system. And that I will get into in my next lecture when I talk about algorithms. So, for example, if you have a quantum computer set up with a C0 gate and a Hadamard gate, these two represent the act of measuring. Okay, so this is how you represent a quantum circuit diagram in a quantum computer for two states, and these are the gates, and these are the measurements, and then you measure here, and these are the measurements. So these are the four Bell states. These are the representation of the four Bell states that you get, where this is the C0 diagram, and this is just the superposition. This is the Hadamard, and this is just the addition gate. Okay, so these are the four Bell states, diagrams for the four Bell state. Now, so now what I have shown you is something which is called a simulator, okay, which is a mathematically exact form I've just shown you, and it tracks the full quantum state, and it scales exponentially. It dies quickly. It can only go for 30 to 40 qubits when you do it actually. Then there is the emulator, which approximates hardware behavior. That is, it includes all the noise that actual hardware will have, and it's used to test algorithms realistically. It's less exact, but more practical, because here the thing is that a simulator is an idealization of the situation where there is no interaction with the environment. Here you try to model the environment in certain ways, and then there's the real quantum hardware, which is the actual system that you're working with, which is going to have all sorts of noise. I mean, that is why you need very cool environments, and so you don't have thermal noise, and then you have, you don't even want any noise from passing equipment, and so what you have is the simulator is the idealized physics model. The emulator is the reality with a few coffee stains, and here is the actual coffee machine. Okay, so this is the difference between what we do, which is simulator, and what actual experimental quantum optics people do, which is actually people, mostly now people in China, which is actually make the quantum computer.
I think India also we have a quantum actual quantum computer right now.
Yeah, well, we have the makings of one at RRI also. And
so how many qubits is that?
I actually, at the moment, I don't know. Okay. I don't think that it's actually simulated anything. But what I do know is that in ISA Mohali, they have built up a very nice quantum computer with NMR, with nuclear magnetic resonance apparatus, and they have tried to simulate some systems which actually we proposed at one time, and but they are only able to deal with a few qubits, not large systems. Okay, so they're only able to. I'm not sure exactly how many qubits.
There are different hardware implementations. I attended a talk recently.
That one is one of the NMR ones, which is
NMR and traps.
Interesting.
I think so. Right. Yeah.
Next, when I come to the actual quantum computers and where they are, and talk about the hardware, then I will talk about this, which will be in next week's lecture.
So when you're talking about this block sphere and the qubits, there are always two-state systems, right? It's always a two-state system.
Yeah, two-state system, except that, but in the later lectures now,
Yeah,
I
but
will talk
that is basically a Hilbert space in two dimensions. Is that
in two
right?
dimensions. Yeah,
No,
and
but
all
in
the gates
principle,
are 10.
if you have many, I think that's something that you had proposed also, right?
Yes. So what we were, because we were neutrino physicists and we found that neutrinos come in three states, we proposed Qubit systems, and then other people have proposed Qubit systems with spin, when they have spin, higher spin particles, then, spin 3 by 2 particles, then you can have 4-state systems, which are called Qubits. And in principle manufacture all these systems, but they're not very stable. Neutrino systems, of course, neutrinos are very difficult to control, and so therefore that is something that we are doing. We can do an emulator very nicely, and the systems have been emulated, but not emulated. I guess it's simulated.
Simulated, yeah.
Yeah. So because now we have to distinguish between simulator and emulator. So they have been simulated, but not emulated even, or the actual hardware will be very far away.
You said difficult to control, but they're also would be stable, right? Because they
be
don't
very stable and very coherent. So they would be very little in those systems. So they would be very efficient if one could do it.
So that's the attraction, if you're able to.
Yeah, that's the attraction. Highly coherent. Unlike light even. I mean, because they don't interact with anything. So no noise can destroy them, Whereas light does interact, and so, laser beams, etc., can be the same. So those would be very ideal systems for that. So the one that is actually functional is this IBM Transmon qubit, and so as I they are with two non-interacting energy levels of atoms that they've been made. So these are, but they're they have. So it's like an artificial atom, right? It's two states being the ground state and the excited state of an atom. It's called a Transmon qubit. That's the IBM one. The newer ones are more interesting. They are based on other types of spin systems called Majorons, which are very interesting spin systems in which particles and antiparticles are the same. And they're topological. They're based on topological quantities, and so they are more interesting. And I'll get into that later. But for now, before I will say that most people who are listening to this can get a temporary account on something called the IBM Qiskit, and they can use that, and they can simulate a few systems. They can do it only for about 1 minute, which is a lot actually. You can use the simulator for 1 minute free. Okay. And this is how you do it. You go to the IBM Quantum website, you visit IBM Quantum Experience, you sign it up, it creates an IBM ID, you fill your details, and then you go and you can get you can go and you can construct your own circuit. It lets you build up your own circuit, and you can, create a Bell circuit and look at it for yourself, and you'll see how fast it is. I mean, you can only have it free for 1 minute, but that's a lot. A lot, because you can just see, here I was sitting in Kanpur with the computer for days, and here within 1 minute you can execute many circuits and go and see for yourself. See for yourself. So this is an interesting thing that anybody can do, and then you can see the power of the computing yourself. And so, as I told you, that we were just talking about the fact that here we were just using two states, 0 and 1, because we are studying neutrinos. And they come in 3 states, and a neutrino is superposition of all these 3 states. It's sort of natural to think, oh, can't we use the neutrinos for quantum computing? So, and as I said, in principle, as a simulator, I can do it, but actually doing it is very difficult. But let me just what in principle happens when you have three states, 0, 1, and 2. Okay. And in neutrino physics, these are called three flavor states. But I won't go into that detail right now. I'll just say that neutrinos exist in three states. They are the electron neutrino state, which is a 1, 0, 0 state. The muon neutrino state would be the 0, 1, 0 state, and 0, 0, 1. So you see, there are three states rather than 1, 0, 0, 1, just 1 and 0. There are three states in which the neutrino exists. And, okay, so we can label each of these three states 0, 1, and 2. So if we initialize it into this state, we can apply a Q-trit Hadamard-like gate, which creates a superposition. And we can also have a Q-trit controlled gate, which will entanglement. Okay, so this is what a Q-trit entangled system looks like. So what will the Q-trit, so if you have three states, 0, 0, 0, 1, 1, 1, 2, 2, 2, three states of the system, then a Hadamard gate will create a superposition of these three states. And then the Q-trit controlled NOT gate, C NOT gate, will then, if it's 0, then it remains 1, 0. If it is 1, then it goes 2 is to 1. If it's 2, it goes from 0 is to 2. So you can have cycle operations which change, and you can make the equivalent states for three basis functions. And it's a little bit complicated, and when you perform these operations, you have to, the rotations on these states are performed by matrices, which are called eight matrices, which are called Gell-Mann matrices, because they were introduced in unitary matrices. That was the representation of when you have three states of the system. And so the unitary 2x2 matrices are called something SU2, special unitary 2x2 matrices. In this case, the symmetry or the matrices that you use are representations of 3x3 matrices, which are SU3 or special unitary 3x3 matrices. And those matrices then give you the general unitary transformation or the general gate for 3x3 matrices. And I won't talk about it much now because it's very complicated. We'll do it later if I have time. But, here's an example of a circuit which was made on the IBM computer for three. Actually, you can have 2 qubits there. So you can have 4. We made one redundant and did it for 3 to show how a neutrino evolves. This is a matrix which shows how a neutrino evolves in space. And these are the various unitary matrices and gates that are used with the Hadamard. It's a little bit complicated, but I just want to show you that you can generalize these systems to more complicated systems, and therefore you can get computers if you can do that. And basically you would have to avail of higher spin systems, like more than electrons and atoms, other spin systems to do that. And once that type of hardware gets into place, then we are just looking for more and more improvement on the calculational ability of quantum circuits. So basically, what superposition allows us to do is have something called quantum parallelism. That is, allows us to have multiple computations in parallel. So exponentially, it increases the speed for certain problems. And qubits can be entangled, meaning the state of one qubit is directly related with another. It enables faster information transfer and more efficient computations. And quantum interference, I will deal with in the next um, installment, in which I will discuss various algorithms which are actually speeded up by the quantum process, which are the Grover's and Shor algorithms, which are one of the reasons why these computers are now being taken seriously, especially by number theorists. So I will stop here.
Yeah. So this.
And continue.
Yeah. I think there will be a good place to stop, and then we can continue next time. Yeah.
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 So I will stop.
Yeah.
Thank you.
Thank you very much.
Okay.